So we're on Monday. We have a homework due on Wednesday. How's it going? How many of you have started working on it? Is it too hard, too easy, too much, too little? Too little and too easy, huh? I'm sorry?
Hard but worth it.
Hard but worth it. That's good. Okay. Any other comments?
It isn't especially complicated, but it takes time.
I'm sorry?
It isn't especially complicated,
But it takes time. Well, the question is not so much whether it takes time, but is it whether it's time well spent. That's what I would be interested in.
well,
Seeing my kids having the years coming home with completely mindless things that take hours, I'm very sensitive to this issue of homework that is not worth its time. So it may be hard for you to evaluate sometimes. It may be that you think it's not worth it, but in the long term it is. But in the other direction, it's pretty clear. Right, I know. But in the other direction, it's clear. If it's clear to you after you've spent a couple hours, oh, I understand it better now, then it's probably worth it. Okay. Gear. Did I ask you already if you prefer thick gear or thin gear? It's a very democratic classroom. Did I don't remember if I asked you already. Thick or thin? Chalk, chalk. Oh, I called it gear. I used the Hebrew word for it. It's chalk. Thick chalk or thin chalk? I don't even have thick chalk here, so I can't even. I'm surprised. It's usually thick chalk here. So I can't give you the choice. I only have thin. Something I don't think I told you before, but it's useful to know. When you do statistical estimation, in addition to the issue of point estimation and interval estimation, the kind of tasks that we encounter in language technologies and in machine learning in general tend to fall into one of what I call three categories. One category is when you're trying to learn a function that maps some input space into a set of categories. Category 1, Category 2, Category K. And this is a fancy way to describe classification. So alternatively, you can say that classification is the process of learning to map some input into one of a finite set of classes, typically a small set of classes. In a special case where k equals 2, you get just two classes, C1 and C2, or yes and no. You basically get binary classification. When you hear the term binary classification, it does not refer to anything binary about the input. It refers to the output. The output is binary. A variation that often comes up is what if every input is mapped into potentially more than one category? So an overlapping categories or overlapping classes. In that case, you can think about it as instead of a standard mapping into k categories, you can think about it as k binary classifications. So every input gets decided, does it belong to this class or not? Does it belong to that class or not? And so forth. All of this falls into the set of classification. Rebooted it. Is it better?
Yeah.
1, 2, 3.
We're good.
Okay. Do you know what the name for this is? Not Lawrence. I'm sorry?
Regression?
Yes, this is regression. Regression is a fancy word for learning and mapping into the real numbers. Not just a fancy word, but a very misleading word. It's a real misnomer. There is a reason it came about, but that's not the way to think about regression. The way to think about regression is you're learning a mapping from some input space, could be anything, into a number. The fundamental difference between these two is what you're trying to optimize. What do you try to optimize in the case of classification? Those of you who take my machine learning class have seen that, so yeah, classification error rate. So goal, minimize classification error. Classification error, or error rate. The rate at which you're misclassifying something. So the assumption or the hope is that most of the time you'll classify correctly, maybe. That would be your accuracy level, how often you do it right. Of course, if it's binary classification, you hope that it's at least 50% of the time. In fact, it will be more than 50% of the time. But if it's a classification into 100 different classes, then doing it even 10% of the time correct might be an achievement. One minus that is the error rate, so the rate at which you make mistakes. The important thing is that if you missed the correct class, it doesn't matter which other class you chose. There's no structure usually in the classes. They are just a set, and either you got it or you didn't get it. Of course, there can be variations. The sets can be sitting in a row, and if you miss one of them, you'd rather be close to the other one. But that now it becomes a little closer to regression. The simplest case is in classification is that the classes have no structure to them. Either you got it or you didn't get it. If you didn't get it, it doesn't matter what you guessed instead. Sure. So it does have the light on, but I'll just... Okay. What is the thing you're trying to optimize with regression? Still not good? It's good. Okay. What is your measure of success with regression? Are you hoping to be correct most of the time? No, you're not really hoping to be correct. The mapping isn't to the real numbers. The chances of getting the correct number exactly are often close to zero or zero. You want to be close. There's a measure of closeness. So what you're trying to optimize, what you're trying to minimize in this case, goal is to minimize the distance from the truth to the guess. And the most common way of defining this distance function is square, right? So that leads to the mean squared error measure. If the distance is squared, squared error, then this leads to the mean square error measure. Let's square the error, and what's the average value of that? But you can decide the distance could be anything. And specifically, you can express this in terms of a distance function that gives you a value of 1 if you got it wrong and 0 if you got it right. It's a nonlinear kind of function. So even though they measure somewhat different, okay, let's start with the differences. They measure somewhat different things, and as a result, whether you frame something as a classification or a regression problem could change the result. And something that would be optimal under one measure might be suboptimal under another. But they're still somewhat similar in that you're learning a mapping. What changes is how you evaluate the quality of the mapping. Contrast that with the third thing that you might want to do. And that is learn a mapping from X to the probability of X. What I mean by that is learn a mapping that, given any possible input, gives you out the probability of that input. So there's no underlying mapping from one space to another, like from the space of inputs to space of categories. Instead, there's just one domain, X, which I'm representing here in one dimension, but it could be high dimensional. And you're trying to learn the density function of the input that comes from it. Density function, if it's a continuous space. If it's a discrete space, you're trying to learn the probability distribution. But for whatever reasons, often people think or talk in terms of the density function. So this thing is called the density estimation problem. So we have classification, regression, density estimation as sort of the three things we might want to do often in language technologies, as well as in many other areas. Now, how could you go about doing density estimation? You're getting only a sample. So the sample might look like this. I'm going to put a line of equal height for every sample point I got. So these are all the sample points you got, and you might decide to model them like this, to kind of smooth them. Or you might decide that they came from a parametric family, like a binomial, like a Gaussian distribution, and then you're reduced to finding the mean and the variance. So there could be many different methods you would use, some of them parametric, some of them not. But the idea is that you're given a sample, and you're using it to estimate the probability not only of each one of the events that you saw, but also of any event that you did not see. Now, in language technologies, usually you need to make decisions, like what to translate into, what to present as output, how to annotate the text, who to send this message to, what the question is to the answer, what's the answer is to the question, which documents. You have some hard decision boundaries. You would think the decisions would be better supported by classification. So often, let's say your task is to do topic detection. You want to know what topic is in the current tweet. Well, you could write a classifier that takes as input lots of tweets, and their labels the correct topic, and tries to somehow generalize from that. You can do it without resorting to statistics, without thinking about it in a probabilistic framework. What you would be doing then is called discriminative, a discriminative method of discriminative training, and your goal is just to create the classifier or the discriminator. Alternatively, you can use the source channel paradigm, which we've done here, and describe your decision as finding the maximum posterior. Right? So let me write it up. Task, topic detection, which means take a document and map it into a topic from a small set of topics. Topic I, where I goes from, say, 1 to 10. Two ways you can go about doing it. One is a probabilistic framework. Probabilistic way, also be called, well, we'll talk in a minute about what it's called. And as you decide that the topic, the winning topic, is the one that maximizes over all topics of the posterior of the topic given the document. Right? We've written that many times, and that can be written as argmax over all topics of the product of the prior of the topic and the likelihood of the document given the topic. Right? You should be very, very comfortable with this. We talk about it all the time. The second method you could use is discriminative training. Discriminative training, call it, which is directly learn a mapping directly learn a function, a mapping from doc to topics that minimizes error over training data, over the training data. So the training data is labeled examples of documents with the correct label, the correct topic. And you can think of trying to find in some space of documents, in some space of mappings, come up with a particular mapping that maps correctly all the training data, or as much of it as possible. And you can think of overfitting that could happen here, and lots of issues. This is a generic machine learning problem, but this does not go through any kind of probabilistic interpretation. This method goes through a probabilistic framework, assumes that there's a prior and there's a likelihood, and now it boils down to estimate these two. These are both density estimation. Estimation from data. From data. So here's a case where you have the same task, and you can solve it in two different ways. One way is casting it as a probabilistic framework, in a probabilistic framework, and then ending up with having to do two density estimations. One density estimation you estimate just from the labels, right? You don't need the actual documents. You just need to know the prevalence of the labels, how often each topic occurs. But it's still a standard density estimation of a distribution. And the second one, you're trying to, it's more complicated. You're using the label data. You're breaking the label data into different topics. And within each topic, you're building a density estimator for the document. In the second method, you do none of that. You're saying my goal is to minimize the errors or maximize the correct classification of future data. I'm going to do that by trying to find a function that does the best job of that on the training data. And maybe some held out data, and maybe I have to worry about overfitting, but that's basically what I'm going to do. Not going through probability at all. Which method is better? Thank you. Okay, it depends, of course. So what does it depend on? What are they better at?
I guess it may depend on whether you need to estimate
Whether you need to estimate probability of note. If you need to know the probabilities of these things, then obviously you should prefer the top one, because it does that for you. But why would you need the probability? Oh, you mean the probability of the topics? Yeah. Okay. All right, that's good, actually. It depends on whether you want to know the posterior or not. You just want to know who's the top one in the posterior, right? Because here you went through, in principle, at least conceptually, you calculated the full posterior distribution. Given the data, what is the likelihood of each one of the topics? And then you did a maximization over that, or argmax, and you found which one is the most likely, and you returned that as your result. But if all you cared about is which one is the most likely, you didn't really need to know by how much. If there are 10 different topics, and the most likely topic is 11% posterior, and all the others are 9 point something, that's one scenario. Another scenario is when the most likely one is 99%, and all the others are a fraction of a percent. Right? The posterior can be extremely peaked around the winner, or it could be almost completely flat, and the winner is just by a little bit, or anything in between. So do you care which situation you're in? Is a good question. If you care, then you should definitely look at this, because there's much more information here than just knowing who the winner is. So for example, if you're going to bet based on these results, you may want to do this to know how much to bet, right? To know how much you trust your answer. Very often when you use language technologies, you want to know not just the best possible guess, but how good that guess is. So a classic example is speech recognition. up until the early 90s, all speech recognizers in the world, all they could do is give you the best hypothesis. But they had no sense of how likely they are to be correct or not. And it was not straightforward to modify them to know or to be able to give information on how correct they are. But it was considered desirable, so a lot of effort went into modifying them in the 90s to put a secondary layer that looks at how the recognizer works and says, in this part of the signal or in this particular sentence, chances of mistake are quite high. Whereas here, we're very sure chances of mistakes are low. So this is, we call that a confidence level, or confidence notation, or a confidence signal. It's a secondary signal that looks at the first signal and says, how likely is that to be right? So to do that, you need something like this. It sometimes comes out of this in this function. And it depends on the details of the function. Sometimes you can build a function that tells you, if you think of this function as a decision boundary between topics, you can think of how far a point is from the boundary as a rough measure of how confident you are in it. But it's not a probabilistic interpretation. It's not necessarily linear with that distance. It could be that when you're very close, there's significant uncertainty, but once you're past a certain threshold of distance, you're fairly confident it doesn't get significantly better after that.
Although some discriminative models also end up estimating exactly the same things as the probabilistic ones.
You can take discriminative models and
For example,
deform them.
translation, in a discriminative framework is exactly what it is in generative one, except that it's a log linear model, so you're taking not only the language model and the probability of the translation model, but all sorts of other features as well.
Right, so if you use a log linear model, you are explicitly training for probabilities.
But it's still called discriminative, right?
Maybe,
So it's
yeah,
somewhere in between.
maybe. So you don't use, so let me introduce another terminology that is relevant, and maybe that would set it apart. You can ask whether your model is generative or not. That means whether you built your model based on some kind of a mechanistic process of how the data was generated. So the source channel model is a classic example of a generative model. It's a very simple generative model. It says there is a prior distribution, something comes out of it, and then it undergoes transformation, some distortion in the channel, and comes out the other side. And that gives rise to this Bayesian classifier. But there could be much more complicated generative models. For example, how is a document generated? Well, here's a story how documents get generated. First, there is a prior distribution over needs to fill the space in the magazine. And then there's a distribution over which editor was in charge that day. And based on that editor, there's some kind of thing that combines the need and the editor to decide on which topic they will choose stochastically. And then based on that, based on which topic was chosen, there's some kind of stochastic distribution over which journalists will be called on the phone that day and say, get me an article about this topic. And on and on. You can build this whole elaborate story of how these things get decided. And when you get to the journalist and when they decide on a specific topic, you can say, okay, the journalist then comes up with an outline. There's some distribution over outlines, and then paragraphs, and within the paragraph, all the way down to the words. Okay? Obviously, it's very elaborate, and we can never expect to fully parameterize everything there. But the idea is that you can, certainly in physical domains, there is definitely a way to break down things mechanistically, why they happen a certain way, what caused what, in a stochastic kind of way. And once you do that, once you use a generative story, you can write down the probability distribution that describes the different components of the generative story and go about estimating their own distributions by estimating the parameters and so forth. This usually goes with this. Generative modeling, or generating story, or generative story. Now, back to your example of machine translation. It sounds like this is not generative at all, what happens there. It's discriminative, but So the last step, or one of the steps, is passing through a logistic regression that gives you posteriors, things that can be interpreted as posteriors. So it's not here, but it does have elements of probability.
In the probabilistic way, for estimating the likelihood, do we need training data here also?
Oh, of course, for estimating this. Yeah, that's, you need, in fact, you typically need a lot more training data than for the prior. The prior is usually easier. So back to the question of which one is better. Certainly if you want, if you're a true Bayesian, you will not even dream about this, right? Because a true Bayesian wants always to have in their hand a posterior, an entire distribution over all possible explanations, all possible causes, all possible values. But even if you're not a true Bayesian, but if you're thinking that you will need to do, you're not only making this one decision here, but you will need to do something with this particular text further down the line, maybe some other module written by your colleagues across the hall or across the country would want to use what you did. If you give them this, you give them something much richer that they could then use to make decisions down the line. If you give them just your decision here, there's less information in there. So it's less rich. On the other hand, all right, before the other hand, here's another way in which this is good. If you could somehow get optimal estimates here, like ideal, theoretically correct estimates, the true distribution, then this method of selecting the winner is guaranteed to be as good as any other method or better. You cannot do better than the Bayes error if you have the true prior and the true likelihood in your hand. I think I mentioned that in an earlier lecture. If the data really behaves exactly the way you think it does, your generative story is correct, and your estimates are correct too, they're perfect, then this is the best you can do. You shouldn't do anything else, because this is the optimal. In the real world, of course, both of these ifs may not hold. Your description of how the data is created is usually a simplification that throws away a lot of information. And your estimates of the probabilities are usually, as you saw when we discussed estimation, are far from perfect. So under these conditions, you are making your decision sort of indirectly by making lots of assumptions. And as a result, the outcome you get in terms of classification rate is not going to be as good. So if the only thing you care about is the classification rate, and you will not need to know anything beyond that, you're typically, speaking very, very roughly, better off with a direct classifier, not going through the probabilistic framework. Just go directly for optimizing the classifier. Again, don't take it as always, but often that's the case.
Is there any relationship to the amount of training data that you have to choose which framework you would want to?
Absolutely, absolutely. So which one do you think would need more data? I'm sorry? First one, the Bayesian, yeah, would typically need more data. Again, I'm saying typically. I mean, there's no, here I didn't tell you how you're going to do that. I didn't tell you what space of functions you're going to consider, so it all depends on that. But generally speaking, in the real world, in real problems, discriminative models would have fewer parameters and would be simpler in some sense, but maybe harder to understand in another sense. A lot of effort went into trying to explain discriminative models in an intuitive way, the way this can be intuitive. Thinking about them as creating decision boundaries in a high-dimensional space. So if you think of your input as living in some high-dimensional space, the simplest way to create boundaries in that space is through subspaces like lines or linear separators. Okay? So a lot of work goes into understanding the properties of linear separators and what happens if your data is linearly separable or not linearly separable. Well, what if it's not linearly separable in its original representation, but it could be transformed into a different representation where it is linear separable. And that's what leads to all the sort of support vector machine and other classification methods that are based on a transformation of the representation through a kernel, which is designed to try to maximally separate the data so you can put straight lines through them. So there is some theory there, but it's not really probabilistic theory. It's something a little different. Often it works better, and I tend to think about it works better because it optimizes directly the thing you care about. When you estimate things here, you need to come up with some kind of optimization measure of how can you best estimate it given the finite amount of data you have. What kind of estimators do you want here? Do you want them to be unbiased? Do you want them to have low variance? Do you want them to be asymptotically consistent? What kind of estimators are better here? And we're not sure. And whatever we chose here, it doesn't guarantee us that that's the optimal choice for reducing the classification error rate. Here, we know we're optimizing directly for the thing we'll be tested on. So this is like studying for the test. Okay, let's go back to MLE. I want to do one more example with you, and it's in your homework, so I'm doing some of your homework for you. But that's okay. What I'd like you to do is don't take notes, just follow it, and then do it yourself. That'll give you the best practice. We did one example of deriving a maximum likelihood. What do I want to do? Okay, a maximum likelihood estimator for the binomial distribution. Let's do now for the Gaussian distribution. Okay, so X is distributed Gaussian, or no, we say normal Gaussian, or the same thing, with mean mu and standard deviation sigma, or sigma square, which is a variance, means that the probability that X takes on a particular small value X is some constant times e to the negative x minus mu squared, x minus mu squared divided by 2 sigma squared. So let's first look at this. This is a distribution that's centered around mu. And as you move away from mu, this grows fast because it's squared in a symmetric way. It's symmetric around mu. And because it's negative, I can put the negative here, that means it falls down very fast. So it looks like something like this. It has a tail, a non-zero tail, goes on to infinity. How fast the tail goes down, I can't say fast or slow. This is the yardstick for how fast all tails go down. So a distribution that has a tail that goes down faster than the Gaussian is called a thin tail distribution. A distribution that has a tail that goes down not as fast as a Gaussian is called a fat tail distribution. So the Gaussian, by definition, is neither thin nor fat. It's the standard. So here's mu. And this roughly is sigma. And hopefully you know that in a normal distribution, the area from 1 sigma from 1 sigma below to 2 sigma to 1 sigma above captures 66% of the mass of the distribution. And sorry, 60.
69.15 if I remember the number right.
60 what?
69.15.
69.5. That sounds like a lot. I thought it was less than that. Anyway, it's in the 60s, which this seems about right. I don't know, maybe not, maybe to here. And if you go another standard deviation, you're up to 96%. And if you go to 3 standard deviations, you're up to 99 point something percent. So these are useful numbers to remember. So this is for a particular value of x. Now, the constant here is 1 over 2 pi, square root of 2 pi times sigma. Okay, so now the problem is, given your training data, which is from x1, x2 through xn, estimate the parameters of the Gaussian, mu and sigma, or sigma squared. We like to write sigma squares because it's a way to remind us this is this is a variance, it's a positive quantity. And sigma itself is also usually measured as positive because it could be, it's a standard deviation. So we're going to solve a slightly simpler problem, the problem when the sigma is known. It's fixed and known, and you only need to estimate the mu. But the method would be the same. The formula in the end would be a little different. So to remind you, the way we go about deriving maximum likelihood estimates is by writing down the maximum likelihood condition. And maximum likelihood condition says that the estimator, mu, maximum likelihood, is the one that maximizes over all possible mu's the likelihood of the data, x1 through xn, given the part that we're trying to maximize and the part that we know. So this we know, but this is a variable. So let's write it down explicitly. It's argmax over mu. Now we're going to make use of the fact that the data was sampled independently. That's important, but you can derive the maximum likelihood estimator even in conditions where it was not independent. If it's not independent, the likelihood function might be complicated. You might write it as a chain product of the probability of the first item times the probability of the second item given the first item, and so forth. And that would be the case if you have some kind of a Markov chain where you took a step and then depending on where you ended up, you took another step and so forth. But in this case, the data is derived independently and all x's are distributed identically based on this distribution. So because they're independent, we can write the likelihood function as a product of the likelihood of each individual data point. So it's basically a product of all of these things, with when x going from x1 to xn. So I'll write it as pi, I goes from 1 to n, 1 over 2 pi sigma times e to the negative xi minus mu squared over 2 sigma squared. Now the important thing is to notice that the variable here is the mu, not the x's. The x's come from a finite set of data. What is unknown is mu. Now this looks like a mess. How do you find the value of mu that maximizes this? But it's actually not so hard. First of all, this part doesn't have mu. It's a constant. So it's a constant in all of them. It doesn't participate. Cross it out. Same trick, if you remember, we did this trick with the binomial distribution. It was n choose k that we got rid of. The second trick, we're going to use again the same trick that we used in the binomial distribution. And that is, instead of maximizing this product, we will maximize the log of the likelihood. So this converts this into argmax over mu of the log of this. So the product becomes a sum. I goes from 1 to n. Sum of the log of this. And the log of this is negative xi minus mu squared over 2 sigma squared. Do you see any other constants we can take out?
Minus 1 by 2 sigma squared from the sum.
The minus?
You
Sorry?
can take it in front of the sum.
I can take the minus in front of the sum, okay. That's good. What else? Yeah, this is a constant, so I can get rid of this. So now, instead of finding the argmax with a negative, I will get rid of the negative and look for the argmin. So this becomes argmin over mu of the sum of xi minus mu squared. Now I'm ready to take the derivative and equate to 0. Derivative with regard to what? With regard to mu. It's all about maximizing or minimizing mu. So I'm taking the derivative of mu. That's basically a sum of quadratic terms in mu. So this becomes sum of, I goes from 1 to n, the derivative of mu of this particular thing for a particular xi. And the answer there is 2 times xi minus mu times the internal derivative of this, which is -1. So you got negative here, -2 of this, and all this has to equal to 0 now. Since it has to equal to 0, I don't care about the -2. I can cross that out too, right? It's a constant. So I get that the sum of xi minus mu equals 0. That means that if I move all the mu's to the other side of the equation, means that the sum of xi equals n times mu, right? And therefore, mu equals 1 over n sum of xi. This is our maximum likelihood estimator. It is a function of the data of the xi. And what is this known as? Sample mean. So again, we've spent a lot of time to prove what every high school kid knows, that if you give them a bunch of, a sample of numbers, and you ask them, what is the mean of the distribution from which it came? They don't think very hard. They just take the mean of the numbers and they say that's the answer. And of course, we know that's not the answer. This is just an estimate. And it happens to be the maximum likelihood estimate. And that's true under the Gaussian assumption. Under other assumptions, it may not be true, although often it is true. So we did 2 examples. One of discrete data, binomial distribution, and one of continuous data, Gaussian distribution. You need, in your homework, you need to redo this on your own, and also to do another example, exponential distribution. And feel free to do others too. That's fun. Questions?
Why did you make it equal to 0?
Because I took the derivative. So in order to find the maximum or the minimum, I typically, after I simplify as much as I can, I take the derivative and equate to 0 to find the optimum. And then to be completely pedantic, I need to take the second derivative and show that it's negative, so that it's a maximum as opposed to positive, that it's a minimum. But that's just a standard way of solving for maximum or minima, is take derivative and equate to 0. I did that in the binomial distribution as well.
How do you know when the derivative is 0, that is the point where the function gets the minimum?
And not the maximum?
Yeah.
Well, to know that for sure, the standard way of showing that is by taking the second derivative and showing that it's negative. A negative second derivative corresponds to maximum. If I took the second derivative here, I crossed out a lot of negatives and positives. So actually here I'm looking for a minimum. So I need to show that the second derivative is positive. And you see there's a minus here and a minus here. All I care about is the mu. So the second derivative of this with regard to mu is 2, basically, right? This times this times this. So it's positive, and therefore it's a minimum. A couple, yeah.
You said that your mean is correct under the Gaussian. How would you know that the assumption to use the Gaussian is correct assumption?
How do I know that my assumption of use the Gaussian is correct? In general, I don't know. And it's a very important and deep and open problem. How do you know that your assumption of the function is correct? There are some tests in statistics called goodness of fit tests that would try to answer the question for you, and they answer it very coarsely and roughly. They don't give you a clear answer, yes or no. They just say it's likely to be, it's not likely to be. The idea of these tests, so these are goodness of fit tests. Suppose you think your data came from a kind of a Gaussian distribution. If you had infinite data, you could just plot it on a density plot and see whether it looks like a Gaussian or not, right? If you had infinite data, then it would have to look exactly like a Gaussian. Since you have finite data, you really can't do that because you'll have fluctuations, but you can break the Gaussian into chunks of, let's say, 10% of the probability mass. First 10%, second 10%, let's say first 10% is long, second percent is a little shorter, third 10%, fourth 10%, well, fourth should be up to here, I guess. Fifth 10%, sixth, seventh, eighth, ninth, 10 equal mass amounts. And then take your actual data and throw it into these buckets. And ask yourself, if it were really distributed as a Gaussian, I would expect a uniform distribution between the buckets. Because it should have 10% in this range, and 10% in this range, and 10% in this range. Does it really have a more or less uniform distribution? Okay? And that you can use this trick not just for a Gaussian, for any probability distribution that you suspect. You can map the percentage, the cumulative distribution of one function to the empirical cumulative distribution of the sample. So I didn't give you all the details, but this is the essence of it, the gist of it. Something else I wanted to tell you. Let me look at my notes. Oh yeah, here's at least one other thing. There is no guarantee that a maximum likelihood estimator exists. There is no guarantee that it's unique. You know what? I 1, 2, 3. Okay. In the case of a single Gaussian, there is a unique solution, both to the estimating the mean, and what we have not done is estimating the standard deviation. But as soon as you move to estimating a mixture of two Gaussians, all of a sudden there's no unique solution. There's no unique maximum likelihood solution if you allow the variance to be whatever you want. So there's no bound on the variance. There are actually many, many solutions. Well, I shouldn't say there are many solutions. There are many peaks of the maximum likelihood of the likelihood function in many different parts of the solution space, and none of them are bounded. So you have arbitrarily large likelihoods. If that's confusing, we'll come back to this in a couple of weeks when we talk about mixture of Gaussians. Let's see if I want to say something else. Okay, I think this is it.
In that case, how safe is the best estimator, like by looking at the bias variance?
Maybe you use your prior knowledge or belief to bound the possible values. So let's say in the case of a mixture of Gaussians, if you're willing to bound the width of the Gaussians, namely, and make them not too thin, not arbitrarily thin, then there typically will be a single maximum likelihood. Or at least they will not be unbounded likelihoods, so there will be some locally maximum likelihoods. There are many cases where there are many, many local maxima, and we will not be able to find the global maximum, because we will have to use local search and get stuck in the local maximum. And we live with it many times in many of our applications. We use, we find the local maximum and then we stop. Okay, so now that we know what maximum likelihood estimation is, we're going to stick with maximum likelihood estimation for a while. And the problem is sparse. So now we're going back to language, which is the queen of sparseness. And we're going to ask the simplest question you can ask about language, which is estimating probabilities of individual words. I don't know if it's the simplest, but it's a good contender for being the simplest. So now we have a corpus, given a corpus of word 1, word 2, through word n. I use the word word, so I need to clarify whether I mean word token or word type here. So here I mean word token, okay? N word tokens. So the index I put here, in general BWI, is a token index. I is an index over tokens. It's not universally true that I has to be index over tokens, but in this example it is. I may also have a dictionary or a vocabulary. I use these two interchangeably. And it consists of a set of word types. Now I have a problem how to designate word types, because I use W for word token, and I get very sloppy in that. So I'm still trying to come up with a good system for describing it. Maybe I'll call it W anyway, unless you want to come up with something else. I'm sorry, T for type. I use T for topic a lot, but the problem is, it's not that I'm lacking in letters. The problem is that the same, when I think about it as a random variable, the values it will take would be a value from the dictionary. Okay? So maybe it's uppercase W. Let's think it's uppercase W. And the index, I'll call it J. So when I use J, it would be an index over types. And it goes up to W, I'll call it V, to remind you it comes from the vocabulary. So I like to use V for the vocabulary size. So J, index over types. So now my task is to estimate the unigram. A unigram is a simple, non-conditional distribution over word types. So this bar would mean it's an array, or you can also write it as P of big W, W1, WV. So it's fancy notation for something that you've all probably done in one way or another. What is the probability of the word the? What is the probability of the word Brazil? Any of the other words? So one solution is the obvious solution, the high school solution. It's the maximum likelihood estimator. So what will be the maximum likelihood estimator of Wj? Maximum likelihood based on our data. Our data is this. This is our data. D equals. Say it louder, please. The relative frequency of that word in the corpus, of that word type. So how many times that word type occurred in the corpus, which I will capture with the letter C for count. Count of Wj, and this is a big W, over the number of tokens in the corpus, right? Is this the correct value for the probability of word J? The answer I'm hoping you give me is we don't know. It's an estimator. It is not likely to be the exact correct value, even if you believe that such a thing as a correct value exists. So there's often the confusion with the fact that the whole notion of language as a probability distribution is kind of bizarre, and that we believe it's not really just a probability distribution. But that is separate from the issue I'm bringing up here. So let's assume for our purposes that we live in a world where language is indeed generated from a unigram model. So I'm not talking about the true languages of the world, like English and French and Arabic and so forth. I'm talking about a synthetic language that somebody created with a large vocabulary, let's say 100,000 words, and came up with some brain-dead distribution over it that they don't tell us what it is, but it's fixed and known to them, and they generate words from that distribution. And we are trying to guess or estimate what their distribution is. Okay? So it has nothing to do with the fact that natural language is or is not well described by a unigram. Let's assume that we live in a world where the language that we're studying is described exactly by a unigram. And the only question is this a good estimate? So is this a good estimate of the probability of Wj, of word type J?
It's not if word type J doesn't occur in the corpus.
Okay, if C of Wj is 0, it's problematic, and maybe even not good, because we do believe that all words have some non-zero probability. Let's assume that. Let's assume we're told that, or let's assume that the way the words were chosen is by observing them in some other corpus. So once they occurred once, they might occur again. They're real words. So how bad is it if, let's say, the corpus is very large? It's got 10 million words, word tokens. The vocabulary is 100,000 word types. Some words did not occur at all. So we give them, this will give them 0. Is that terrible? Yes?
For the sake of unigram probabilities, not really, but when you're trying to estimate the probability of the sequence, that's awesome.
Okay, I like that. So if your end goal was estimating this probability distribution, unigrams, you could argue maybe it's not that important. If you gave it 0 and the true probability is 0.000001, okay, not bad, and it's pretty close. But if your goal is different, then the difference between 10 to the negative 8 and 0 may be very large. For example, in practice, it would kill any hypothesis that assumes that that word shows up. So when you combine it with other things in some kind of a generative story, a 0 kills everything, even if you have much stronger evidence later in that direction. So maybe you want to avoid it. We will talk later about information theory and come up with a more general reason why we want to avoid estimating things with 0. I'll give you the spoiler now. The reason you typically in language technology want to avoid 0 estimates is because what we often care about is relative error, not absolute error. And the relative error between 10 to the negative 8 and 0 is infinite, whereas the absolute error is just 10 to the negative 8. We'll talk about it more later. Just start thinking about it. Okay, so I'll have to be careful about the 0 cases. Anything else?
What if you see it only once?
What if you see it only once? Then what?
Are you sure your estimate is a good estimate?
Well, I don't know. Are you?
Probably not.
Why is it not a good estimate? So it's 1 over 10 million, 10 to the negative 9. Do you have a better estimate?
No.
Maybe the absolute value is correct, or good, but as an estimate, but the relative, that may be bad as a relative estimate.
But you don't mean absolute value as in negative positive. You mean the order of magnitude is right.
Yeah, so it's.
Yeah. So maybe the order of magnitude is right, but it could be twice as large or half as large. Or 10 times as large. Right. What about 2 times? Is this better? All right, so a word that occurred 2 times, you estimate as 2 times 10 to the negative 7. And a word that occurs once, you estimate as 1 times 10 to the negative 7. Which one of them do you have more confidence in, or about the same? So do you remember that estimators have variance, right? And one of the things we said about the maximum likelihood estimator is that it's got lots of wonderful properties. It's typically unbiased, asymptotically consistent, it's maximally efficient, but there's always a but. There's no free lunch. Its variance is not that great, especially when the counts are small. The variance is large. So you had 30 occurrences. So the answer is 30 out of 10 million. Do you feel better about it?
Better than 1.
Better than 1. But you pointed out a good point. It's better if what you care about is relative accuracy, like the percentage. Like, do you have to correct it by adding 20% or subtracting 50% or multiplying by 5? Not by absolute distance, but by relative distance, relative error. So in relative error, you would feel better about something that you saw 30 times than about something you saw once. And something you saw 0 times is an extreme case. So keep that in mind, and I'm going to give you a scenario. I took all the data in the corpus and I put it into a table that I call the frequency of frequencies. What it is I put here all the words that occurred once. Count of W equals 1. That's right here. All the words that occurred once in the corpus, and I'll just build a little histogram. Right next to it, I put a histogram of all the things that occurred twice. Count equals 2. This axis is word types. I'm emphasizing types. So this is how many different words occurred exactly once. This is how many different words occurred exactly twice. This is how many different words occurred 3 times. 4 times, 5 times, etc. Here I will find words like fairly rare words, like bamboozled, and I don't know, give me a rare word, aardvark, and so forth, lots of words. You would expect to find this kind of distribution. Namely, there are many more words that occurred once than words that occurred 2 times. And many more words that occurred 2 times than words that occurred 3 times in any natural language, in any naturally occurring language. If you keep going here, depending on how large your corpus is, you might get to a point where no word occurred exactly 47 times, but there was a word that occurred 48 times. Or if the corpus is very large, it won't happen in the 40s, but it will happen in the 500s. Some words occurred 535 times, no word occurred 536 times, but there's one word that occurred 537 times. And then you go all the way to the extreme, there's going to be a large desert of no word occurred exactly this many times, and then the word the occurred a gazillion times. Okay? So it's going to be very sparse here, but I care more about this part. This part would look very nice, nice and smooth. Now, these words have a term for them in linguistics. The linguist in the crowd, Lizzie, are you a linguist or no? You're a philosopher. Where are you? Not here. Oh, there you are. Or a linguist in the crowd. Hepata legum. Hepax, yeah. H-A. I don't know, it's some Latin something or other. But I like to call them singletons. Okay? Singleton is very easy to remember. It's a word that occurred once. Obviously, it's a function not of the word itself, but of the word combined with a particular corpus. And the other thing about singleton is that it's easy to generalize it, and these are called doubletons. And these would be called tripletons and so forth. If there were words that didn't occur at all, I would call them zerotones. It's my own invention. I'm not sure it's common usage. Okay. So now you are given another word from the same source from which you collected the corpus. And the question you're asked is, what is the probability the next word you're given is a singleton? You observe the corpus. The corpus was generated from a unigram, a fixed unigram that you don't know. Large corpus, you collected the data, you drew the frequency of frequencies. Now you're about to observe the 10,000,001 or 10,000,001st word. And before you observe it, you're asked, what is the probability that that word would be one of your singletons? What's your estimate?
The number of singletons over the whole.
Right, thank you. That's good. So we call this C1, number of singleton types, and we'll call this C2, we'll call this C3, etc. So the suggestion here was C1 over, I'm sorry? Vocabulary size?
What you're actually measuring is word tokens here, right?
Right.
Estimating of the probability of word tokens. According to Zipf's law, if you said that every word's rank is about half of its frequency, what
Half? I don't know if it's half. It was,
approximately half?
no, it was inversely related. Let me just let him finish the suggestion. What were you suggesting here?
Oh, I was just going to say over C1 plus C2 plus C3.
Over C1 plus C2 plus C3. All the way through CK. These C's would sum to the total number of tokens, which is V. So it's the same suggestion that came from here, right? Anybody wants to agree, disagree?
Isn't the number of tokens n?
The number of tokens is n. Would you prefer to see n here? Yeah, I would prefer to see n here also. This is a prediction in the space of tokens, right? We're looking at the next token, and we're saying, how likely is the next token to be the word bamboozled? Well, our maximum likelihood estimate, at least, is 1 over n. How likely is the next token to be the word aardvark? Well, our maximum likelihood estimate is 1 over n. So the probability that the next word would be either bamboozle or aardvark or this or this or that, all of these, is the sum of 1 over n of all of these, right? So I'll write it explicitly. It is exactly equal to the probability of the next word being bamboozle plus the probability of the next word being aardvark plus the probability of the next word plus dot dot dot, probability of the next word being the last word in the list here, which I will call Z, 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 Z. One, two, three. This is not an estimate. This is just set theory. It's the probability of this set is the probability of each event in the set. They are mutually exclusive and complementary. To be a singleton, you have to be one of these words, right? And now I'm going to estimate that with 1 over n for the first one and 1 over n for the second one and 1 over n for the last one. It comes to a total of C1 over n. So that's my estimate for the probability that the next event will be considered, will be one of the singletons, will be one of the words that are singleton. Now, I'm actually going to try that. I'm going to collect not a single word, but 10,000 words from the same distribution. Each one of them has this probability, by our estimate, of being a singleton, of being from that set in the left column, right? So with 1,000 words, we consider the expected number of first column words So these are the words that came from here, the word types that came from here. First column word types. Expected in the next 10,000 words is 10,000 times C1 over n. Right? We're assuming that the distribution is indeed exactly a unigram distribution. Each one of these words independently has a probability of C1 over n of being from that column. So the expected number of words from that column would be the number of times I drew it, times C1 over n. This is very wrong. That's not what happens in practice. What happens in practice is that the number that you will find there would be significantly lower. In reality, the number of singletons that you would find, number of words from this first column that you will find here would be much smaller. In reality, much smaller than this. How could that be? Why does that happen? So this is not a fluctuation. Of course, there will be fluctuations. If I sample 10,000 words and I count how many of them were in the first column, I'll get some number. Tomorrow, I'll sample a different 1,000 and I'll get a different number. There will be a fluctuation there. But the answer is going to be very different than this. In fact, it's going to be significantly lower. Could be by as much as 70% lower. I mean, we're not talking about a small fluctuation. We're talking about a huge difference. If you don't believe me, and most people don't believe me, you will write the code yourself, and you will run this experiment, and you will calculate it, and you will find out. That's your next assignment. But the question now is, I'm sorry? Oh, you decided to believe me.
Yeah, I was actually wanted to say that it does make sense because we either see the term or do not see the term, so we're essentially exaggerating and we see it only once, so we're probably exaggerating by the estimate. It's an upper bound, it's very loose upper bound for the actual number of terms.
So the right terminology is not that it's a loose upper bound.
Yeah,
It's biased high, right? That's the right terminology. But by loose upper bound, what you meant to say is that we are overestimating it, but we're not guaranteed to overestimate it. Sometimes we may underestimate it, but on average, we're overestimating it. That's what biased high means. So here's a bit of a conundrum for you. Maximum likelihood is unbiased. And yet I'm claiming that the maximum likelihood estimate applied to this set, produces a very biased estimate. And I'm even telling you it's biased high, and I'm telling you it could be by a lot, by a factor of 3.
This is probably because of the fact that language doesn't follow a unigram distribution.
Nice try, but I'm ready with my reply. This is true even if you do the experiment, not with language, but with some arbitrary unigram distribution. So you're guaranteed that it follows exactly what you tell it to follow, which is what you will do in your assignment. We will use words, but the words there are just placeholders. I mean, it could be anything. It happens whenever you have a distribution over many, many, many types. And the distribution has a long tail. Zipf's kind of distribution.
Don't we have a selection bias here in our selected one?
Go ahead. Okay, what are we selecting?
I was selecting those that appear only once. We don't select like some specific token and see like, okay, let's pre-select it before it actually appears on the collection, and then see how many times it appears. No, we only pick those that does appear, and that creates a bias.
Right. That's the explanation I would like to give. So thank you. Did you want to add something?
Yeah, the set of zero terms,
Uh-huh.
we have a bias low probability.
Yes.
For, and so when we select, when we exclude those, then the rest of the words are going to be biased high.
Yes, that's a very good way of seeing it. So I love both of your answers, so let me rehash them a little bit. What we did here is we selected what our target is after seeing the data. And that's a no-no. That's what led to the biased estimate. So if we had selected, let's say this set has 300 words in it. If we selected at random 300 words from the vocabulary and said, okay, what is the probability that the next word would be one of those? Then the maximum likelihood estimate for these, which is the sum of their occurrences over n, would be unbiased. But that's not what we did. We waited until we saw the data, and then we selected specifically words that occurred once. And that introduces the possibility of a bias, and indeed there is a bias in a particular direction. To see why there's a bias high, consider the fact that if we had done that not with a set of words that occurred once, but with a set of words that occurred 0 times, our estimate, our maximum likelihood estimate would be 0 because they occurred 0 times. All of them together occurred 0 times. And of course, by our construction, this is wrong. They have a positive probability, so we're biased low. So the zero tones are guaranteed to be biased low, and therefore something else has to be biased high. And what's biased high is the singletons, and to some smaller extent the doubletons, and to some smaller extent the tripletons. And there is a high bias that goes smaller and smaller as we go here. When you get to 5 or 6, it becomes almost negligible. 1%, 2%. When you get to 30, it is exponentially negligible. But theoretically, it's still there. What caused that was exactly the fact that we selected our set, our event set. We defined our event set after we saw the data, based on some function of the data, the counts of the data. So when we come back, we will rehash this, and we will tie it to the well-known problem of regression to the means. If you don't know what the regression to the means is, go and Wikipedia it. It's a well-known problem, very tricky, but well worth understanding. We'll discuss that as well. Thank you.